All right, hello and welcome. So, hope you have had a reasonable break and hope uh, that your midterms went reasonably well. We will have a discussion on that when we meet up next. The coming Wednesday. But this is returning to our discussion of Lie algebras and Lie groups. And today we are going to have uh, another lecture on that. I don't remember which number of lecture this is, but yeah, we'll figure that out as we go along. Okay, so let me start by sharing screen. So today's lecture is called From Lie algebras to Lie groups. Okay, so let's do this. So what we have been discussing is that we have been discussing how one can try and understand the algebras. We have focused on SU2s mainly, and I've also told you a few generalities of the algebras. Now, let's turn our attention to Lie groups and how we can go from the algebras to Lie groups, okay? So we start off with a generic unitary operator. This can be written as e to the IH, where H is Hermitian. Now, the generators of SU2, you'd remember, are Hermitian. So an operator, if you take an operator of the form U of theta is I theta A T A, where these Ta are real parameters and Ta are generators of SU2, then this is a unitary operator, okay? Just to remind ourselves, if U is unitary, that means U dagger U is equal to 1, or U inverse is equal to U dagger. So now if you take U as e to the power some matrix M, so it means that M inverse, exponential M inverse is in exponential M whole dagger. That would mean that minus M is exponential M dagger. So that would mean M dagger is minus M. Hence, what we have to do is we have to put in an extra I sign to take care of this minus. So M is IH, where H is Hermitian. So you see, this is how you get a unitary operator. And this is the source of this extra factor of I, okay? It's easy to see that these operators U actually satisfy group axioms. So if you look at theta equal to 0, so this is what is going to be the unit element. There is also going to be an inverse where you can replace theta by minus of theta. You can show that this is closed under multiplication, and you can also show associativity, and this essentially requires a use of this Baker-Hausdorff formula, which you can look up if you're not familiar with. This just expresses the product of exponential of matrices as an exponent again. And so these I leave to you to work out, and maybe I'll set an assignment on this, but yeah, so this should be reasonably straightforward. Now, it's particularly simple when you are looking at these u's in this exponential of these exponents. When you're looking at the j equal to half representation, remember, when you're looking at the j equal to half representation, those are given by our sigma matrices. This is something that we did. So this is going to be given by exponential of e to the I theta a sigma a over 2. So there is going to be this cos theta over 2 plus I theta a cap sigma a sine theta over 2. So this theta a cap is given by theta a by theta, and theta is just square root of theta a squared, if you wish. And if you do this, closure and associativity are actually manifest in this form. So this is something that forms a continuous Lie group because its parameters, this theta, are are also, as I say out here, continuous, right? Notice something very important. These group transformations are periodic, but with a period of 4 pi. Okay, so this, it should start to ring bells. Is that a 2 pi rotation actually results in the reversal of a sign of a vector on which it acts. Now, this has very interesting sort of, consequences for physics and the real world. And for example, what is it that returns, when you take it around by 2 pi, it doesn't go back to itself, but it goes to itself with a sign. So these are objects that these are objects called fermions, and fermions are everything that matter is actually made up of. So you see the fact that SU2s are going to play a very significant role in all of physics, if you wish. So we will see this a little more clearly if you so a little more clearly when we are looking at trying to understand the Poincare algebra at the end of this half, this part of the course when we are looking at group theory at the end. But this is something that you want to keep in mind. So when you are looking at this defining J equal to half representation, the group transformations are essentially, so you see this very clearly. There is this 2 pi, something, this is group transformations are periodic with a period 4 pi. Okay, so another thing that is obvious is that the transformation that leaves if you're looking at an operator as an operator in a Hilbert space, the transformation, this particular transformation will leave invariant the quadratic form z1 squared plus z2 squared. Okay, so so this is in a sense, so okay, so the reason why this is important is that this J equal to half, half representation makes it very clear, why this, SU2 is actually called, SU2. This is the group of unitary transformations in two dimensions. So these are going to be matrices which are, these 2x2 matrices with complex entries, and the fact that the determinant will have to be equal to 1, right? So just to clarify something, when you're using lower cases, that is going to mean the algebra. When you want to use the upper cases, this is going to mean the group. So what we have learned from here is that the general form of this group, so the representatives of this group are going to be these 2x2 matrices, which are given by these entries alpha beta minus alpha bar minus beta bar alpha bar, and this is subject to alpha squared plus beta squared equal to 1. Okay, any group element is sort of represented as a point on this group, what is called the group manifold of SU2. So, and from here, this is clear that this is going to be an S3. Now remember, what is an S3? So so for example, an S2 is something which is x squared plus y squared plus z squared is equal to r squared. So that is an S2, right? So this is an S1. This is an S1, that is an S2. So, and it should be clear that this guy now is an S3. So it is a higher, higher dimensional sphere. And so group element. So this is if you wish, if you're thinking of embedding it, it's going to be something that you're going to embed in 4 dimensions. And so this is a surface in 4 dimensions, and this is sphere in 4 dimensions, and every point on the surface of this sphere is going to be representative of a group element. Okay, so lastly, succession of transformations will trace out a curve, continuous curve on S3. And you'd remember that any sort of curve on S3 can be shrunk to a point. And hence what we'll have is that, S2 as a group manifold is simply connected. So, it might not always be the case, but for at least for the example of S2, this is true. Okay, some funky things about S2, some more interesting things about it. So let's look at the algebra again. Okay, so let's look at the algebra, and now we find an interesting property is that if we change the signs of 2 of these guys, if we change the signs of T1 and T2, and we keep T3 as the same, then the algebra actually stays the same. This is called an involutive automorphism of the algebra. And more interesting thing here is when you actually multiply T1 and T2 by an I. So you define L1, L2 as so L1 is IT1, L2 is IT2, and let's call L3 L3 as T3. Clearly L1 and L2 are not Hermitian anymore. So the algebra has changed in this case. Okay, the algebra has changed. Some of the signs are not the same anymore. This is still early algebra. Okay, you can check that if you were to try and close it with the Jacobi identity, things will go through. But a significant thing occurs here is when we are looking at finding out what the quadratic Casimir is for this algebra. This extra sign is going to show up, and this extra sign is going to show up somewhere here. Okay, so that would mean that you unlike SU2, this changed Lie algebra is not bounded from below anymore. So since Q is no longer positive definite, this spectrum of L3, for example, does not need to be bounded. So you naturally this sort of algebra resides in an infinite dimensional Hilbert space. This algebra, as I write here, is a non-compact or real form of SU2. And if you are thinking about vectors in 3-dimensional flat space or 3-dimensional Minkowski space, this looks very much like this. So this algebra is called SO21 or SU11. Okay, so 1 and 1 is taken into account the sign out there. Okay, so that's that. Representation theory will be much more involved, but we will get a flavor of this when we are looking at the Poincaré group later at the end of this part of the course. Okay, so that was that for SU2. So let's now focus on something else. And let's now focus on orthogonal groups, okay? Now, rotational groups. And we are going to focus on the group SO2, okay? So this is a special orthogonal group. This is the special orthogonal group in 2 dimensions. And this is going to be defined by the set of unimodular matrices, which are real and orthogonal and 2 cross 2. Okay, so we have A as A, B, C, D, and determinant of A is equal to 1, like I said. And you know the fact that it has to be orthogonal is here, so it has to be A transpose has to be A inverse. So what you get is D is A and C is minus B. You can just do this. You can just figure this out just from here. And what we get from here is that this translates into A squared plus B squared equal to 1. Okay. Now this is going to be familiar to you, of course. Now A squared plus B squared equal to 1. It sort of keeps the length of a vector the same. And so this is going to be a rotation group. So the A and B, I mean, in a sense, are going to be bounded by plus minus 1. Okay. So A squared plus B squared equal to 1 sort of immediately says that, you can sort of label this in cos thetas and sine thetas. Let's call A cos theta, A as cos alpha, and B as sine alpha. So this matrix A is given by cos theta minus sine alpha, cos alpha minus sine alpha plus sine alpha cos alpha. And so let's call this R alpha, right? So, I mean, it's very, very straightforward. This is something that you all know, that this is going to form a group, and this is going to form an abelian group. As you know, the rotations on a plane, are going to so these are going to commute, and they would give you an abelian group. So we were speaking about this in one of the interaction sessions, and you guys were asking me, what about this, and what do we have to do about irreducible representations here? So the point is that if you have an abelian group, any irreducible representation actually has to be one dimensional. Okay, so that's the crux of the argument. So the idea, so the point is that this 2 cross 2 dimensional representation is actually a reducible representation. Let's explicitly see this. So the since SO2 is abelian, it's irreps are 1 dimensional. So this the representation that we just came across is reducible. Okay. So now let's look at how this is the case. So let's if you look at this 2 cross 2 dimensional matrix and find what it's what the eigenvectors and eigenvalues of this are, you'd find that these are the eigenvectors, and these guys are these corresponding eigenvalues of these eigenvectors. So these are these are transformations that would be you can look at them as these represent transformations in a complex 2-dimensional vector space. So now you have one so there is going to be something which is spanned by U1, and there is going to be, so in this 1D subspace spanned by U1, R alpha is going to be denoted by this particular complex number, which is e to the minus I alpha. And in the 1-dimensional representation spanned by U2, it is going to be represented by e to the plus I alpha. So you would have explicitly a similarity, transformation that acts on this D of R alpha and brings it to this form. So so that means that you can start off with this and act it on dr alpha, which is this, and what you get is what you get at the end of the day is you are going to get in this subspace it is going to be a to the minus I alpha. In this subspace is going to be a to the plus I alpha. So what we have is we have two equivalent one-dimensional representations of SO2 given by exponential minus I alpha and exponential plus I alpha. Okay. So what is this? So these 1D, 1D irreducible representation is a set of linear transformations from a 1D complex vector space onto itself. And so what is going to happen is that here this u vector is going to be it's going to represent the only unit vector of V, and the transformation is going to be just going to look like this. Okay. For some complex number C alpha. The possible irreducible representations of SO2 are given by exponential e to the ik alpha, where k is all all integers. And each value of k gives an irreducible representation that is not equivalent to one with some k prime. So that should be obvious that you would not be able to transform it to something like this unless these guys are one and the same. Okay. All right, so that is what you have for so this means that the matrix cos theta sine theta, cos theta minus sine theta cos theta is a 2 cross 2 dimensional representation of SO2, but keep in mind that this is a reducible representation and the irreducible representations are one dimensional. We have explicitly shown you this as well. All right. Now we are going to define something which is rotation in 2 dimensions. So this is going to be, so the generator of rotations is going to be given by, so you had this the angle which was alpha, so it's going to be given, so you're expanding this, right? You're expanding this around alpha equal to 0. So the as we had defined before, the generator is going to be given by this expression here. So it is going to be dd alpha of r alpha at alpha equal to 0. If you do this in this cos alpha sine alpha thing, then you'll find that this is given by 0, minus 1, 1, and 0. So this is what A is. Now let's look at this once more, and so let's look at dd alpha of r alpha. So that's this object. That's clearly this into r alpha. So dd alpha of r alpha is A into r alpha, and r alpha is going to be exponential of alpha A. Okay. Now we can try and figure out what the differential form of for the generator is, and then that what will that be? So this is going to be, so you take some form of this. So you start off with f of r, which is where r is at x and y, and this is going to move you to some f which now has r inverse acting on x and y. Okay. I have a little explanation for why this is the case. So this is something that you might be familiar with from things like transformations which are active. So yes. So a little small issue here, but let's make sure that I correct that. So actually this is d of r alpha. Yeah, so what we want to do is I want to show you that d of r alpha, so this is the representation of some matrix r alpha which is acting on f, which is at which is at xy, and this goes to something. Okay, now you would be asking me, why do I have to go to r inverse of xy? So let me try and clarify that. Okay, so suppose you are you are going to be let's start off like this. So we are looking at active, active rotations. So you have linear transformations of a plane onto itself, and such that these vectors rotate by an angle alpha. Okay, so you if you have e1 and e2 as your the uh, basis vectors, then they're going to rotate into something which is u1 and u2. Okay, and so that's what is happening. So what I mean, so this is going to, change, right? So the if you want to bring it back, what you have to do is you have to re-express this. So in a sense, what you want to do, so the w out here is going to be some v1 u1 prime plus v2 u2 prime. Now you need to express these, so you have u1 prime and u2 prime. You need to express these in terms of e's. Okay, so this would, if you do that, so yeah, okay. So I'm not explaining this that well, but the idea is that when you think of this, uh, say suppose you have you have a sheet. Okay, you have a sheet and you sort of heat the end, one end of the sheet. So suppose you have something like this, so and you heat this end of the sheet, but you sort of rotate it to another, as I've done here. So you are going to move, say suppose you have this end of the sheet. So if there is a marked point, so the function, so what we are going to have is that there, so the sheet is going to be, you'll move the sheet, and in this sort of new position, the distribution of temperature that you had for the sheet, which was to start off with, say T of R, now becomes T primed of R. Okay, if you assume that it's the same sheet, then that the rotation will not change the temperature at a given point on the sheet. So what we are going to have is T primed on this R of alpha, on this changed R. So T prime at R primed, if you wish, is going to be equal to T of R. So the numbers, for example, something is at 15 degrees at some point. This is at 15 degrees. Just because you've rotated the point, the sheet, it doesn't mean that the temperature of this point has changed. So there were some numbers that were ascribed to each point, even though the function, function apparently has changed. The numbers there have not. So what this translates into, T primed at R primed is equal to T at T at R. So if you want to find out T primed at R, so what you'll have to do is you'll have to do this inverse operation here. Okay. Similarly, so now we have R of alpha. So F goes to D of R of alpha. So now D of R of alpha acting on F will go to F of R, F primed of R, and F primed of R, as we have seen from here, F primed of R will have to go to R inverse of small r. So that's the thing. So that is why you have this, this sort of relationship here. Okay, this may not be very clear in the way I've tried to explain it. Maybe if you have problems with this, we can try and address this again next time around. But the idea is that you have to relate something which is f where r is equal to xy to uh, f at r equals to this r inverse of xy. Okay, so if you do this, let's see what we get. So we remember that r is exponential of alpha a. So that is going to mean that d of alpha of this is essentially d of r of alpha. So forgive my so notation is d of r of alpha is written as d of alpha. Okay, so that's something that you need to keep in mind. Uh, so this would mean that you are going to so this is going to be so the we want to find the form of this guy A. So this is going to be, now since we are looking at the representation of r of alpha, this is also going to be the representation of the of this particular generator. Okay. Now, in the standard irreducible representations of SO2, we have seen that d of A is going to be ik, right? This is something that we have just seen. So what is happening now? What we will do is we will write this down. So d alpha of f of r is exponential of alpha of dA into f of r. And we can expand this. Okay, so what we will do is that we will expand one. So this is our equation one. So we are going to expand this equation one. So if you do that, so what we will find is r. So this is so we expand this equation one, and we find this. So we just so what we find is that when you do this, there's going to be f of r, and then there's going to be this guy, which is delta x del x or delta y del y. Also keep your next pieces. This is what you find up to this order. And then you also expand out this. Okay, so now you're going to equate them. So f of d alpha of f of r is I dA plus alpha squared dA squared plus f of r and so on. So now what we have to keep in mind is when you're looking at this, for example, so this is going to be r of minus alpha acting on small r minus of small r. Okay, so this again, expanding things out, you'll find that this is alpha y minus alpha squared, right? Over 2x and the rest of the things. In the second one, this is going to, you have to be a little careful with the signs. This is going to be alpha x minus alpha squared y plus the rest of the stuff. So what we will find is if you were to write this down, if you were to expand this again, we will find that f of r is going to be given. So if you equate these two now, then what we'll find is f of r is going to be f of r inverse acting on r is going to be f of r plus this object now. And so you see that this is going to be the representation of my generator is going to be represented in this way. Okay. Now it's also if you were to work in x equal to r cos theta and y equal to r sin theta, it's very simple to see that d of a is going to be given by just del of theta. So remember that we like Hermitian operators at the end of the day. So you can put some i's in front of the a's, and then what you'll have is a will be given by 0 minus I 0, and the representation of a is going to have these extra i's out here. So this is going to be this. So you have a, so this is your sort of well-known rotation, rotation generator, now actually worked out for you in a more sort of sophisticated language, if you wish. SO2, as we were saying, is just something that has, so this is going to be a matrix that is represented by one theta, and so our generator is just del theta. So it's just one particular generator. So there is no algebra to speak of. So that's sort of the trivial, example, if you wish, of what is happening here. So SO2 is also equivalently U1, but okay, so let me not go into that. But so that's what we have. So what we have is these rotations on a plane can be thought about as sort of special orthogonal groups in 2 dimensions. And so we have said a bit about that in this class. And yeah, so if this has been a little too fast, at least the last part about trying to understand how to get this differential operator for the generator, we will revisit this once more when we speak to you guys next time around. So yeah, so that's more or less about it for the moment, and we will see you in the next class. And yeah, all right, so that's that. And in the next class, we move on to a little more, things of a little more interest. We move on to we move on to SO3 and how SO3 is actually related to SU2. So that is what we want to do next time around. And but for the moment, yes, that is going to be it. Thanks, and see you.